Go. Finally got there. Okay. So the stress strain curve we have done some discussion of. We want to make sure that we know the difference between the elastic deformation. So this very first part of the stress strain curve we've seen a couple times. Then we transition into where some plastic deformation starts coming in, and we get slippage of these slip planes that create some boundary related issues. I guess I should probably use a different color there. So slippage along these slip planes that were originally here, these slip planes appear in order to allow for some movement of these bonds without breaking them all at once. We cause that sort of ripple effect like you guys have seen in some of the other demonstrations. As that plastic starts and you relax the load, you still have an elastic region that still has the same slope, because the steel doesn't suddenly become not steel anymore. The steel doesn't have the option of no longer identifying as steel. It's elastic plus plastic deformation. And what that does is creates the conditions for change, a permanent change that happens here in terms of strain. So there's a permanent strain, there's a permanent deformation after the load is removed. So it's very important that those slopes stay the same, but that's the plastic strain, so the amount of strain that is stored plastically. So when you unload them, these planes come back together, but the slip planes are still misaligned. So even though you remove the stress, the slip planes are still aligned. Then if you go back and do it again, you're going to do it again over and over repeatedly. So there's a yield strength, and that's the stress at which noticeable plastic deformation has occurred. So it's referred to as the 0.2% rule. So it's strain of 0.002 or 0.2%. That region is referred to as the yield strength. So when this starts having a sharp knee in the curve is called the yield strength. So at a specific tensile stress, a material will move. It's different for every different grade of material. And some aluminums can have a yield strength that is close to that of mild steels and things like that. So this is part of the reason why they're used for aircraft frames and things like that. They need to be very strong, but also very lightweight. So those tend to be a good choice. So the yield strength here becomes important for ceramics. It's difficult to define. Specifics of processing and manufacturing, there's really not a good range to measure for ceramics and semiconductors. They don't work well in tension. They tend to load and then fracture occurs before the yield does, so they just shatter or explode under tension. That tends to not work really well. Similarly, composites, those can be very, very hard to measure. So there are differences in the manufacturing, differences in the layup. The fracture of the material happens usually before they fail. Let me see if I can find an example, because I think I know of a really good one. Let me see if I can find an example. Let me see if I can find a good example. Um, um, there's a few examples. Trying to see. Yeah, here we go. So carbon fiber nose cone crash test. Uh, that's going to be the best example really that I can show of this. Let me get it past the inevitable ads, and then I'll share this. So notice that it just fractures and sends pieces everywhere. There's a couple other examples. So it shatters and sends shards everywhere. And that's the failure mechanism of these. They don't fail gracefully, they fail explosively almost always. There's another, I think, series of examples. Same sort of thing. Yeah.
Love and happiness. In my old neighborhood. Just got my 817 back, and as you can see, the dry shaft shop dry shaft. I sent them pictures of the dry shaft where it split right here, it unraveled, and then once this came apart, this started wobbling all over around the car.
Yeah, they don't like the failure. So very fast, very explosive. Does not take shock loading well. So the composites are prone to fracture in a very fragile manner. They're prone to fracture. They're prone to detonate and shoot shards everywhere, just because of the nature of the way that these things work. So it's important to understand what exactly is happening there and why. So that's the reason why we don't have a lot of data specifically for these composites. It's just it's very tricky to be able to identify the data for these. So the things like tin are extremely soft. Aluminum, still very soft, very low yield strength. Much higher are steels. There are some various treatments that are listed here. So A is annealed, meaning it's we anneal materials in order to be able to make them softer for making machining easier. Tyler had mentioned there's such a process called work hardening. We're going to learn about that later. Often when you work harden something, you have to go in and anneal it to make it soft again, and becomes a whole thing. So steel 1020 hot rolled is a very mild steel. 6061 aged aluminum is quite a bit higher in yield strength. So this is more like what car parts and things are typically made of, rather than annealed aluminum. They'll often do that for the machining and then age it at the very, very end. So copper hot rolled. So things like copper tubing is probably going to be mostly hot rolled that you'll encounter. You probably won't encounter a lot of cold work, but you're going to see the difference between hot rolled and cold worked aluminum or copper rather in the hardness testing lab, where you're going to do some rolling of some copper strips. So that'll be a hot rolled sheet that then you cold work, and so it can be quite a bit higher. So tantalum is another one that you won't see very often. Pure titanium that's annealed, again, down here below some of the aluminums and steels. So things that you want to pay attention to, but as soon as you have an alloy up there or something like that, or tungsten, which is very much higher yield strength compared to something like molybdenum. We use chrome moly steel. We use 4140 or 4130 is a very common alloy for a lot of internal engine parts. And the reason that yield strength can be very important is even in the context of something like an engine, if you have a connecting rod that's supposed to hold the piston in place, bring it up into the cylinder, compress the gas, and all of a sudden you have something bad happen where the pressure wave hits the piston prematurely, or it's not fully compressed yet, and it's not the connecting rod hasn't moved into its position in the rotation to be able to push down on the crank again. You end up with a lot weaker materials. And what happens with those is they become so much softer that it's very, very hard to actually use. Let me see if there's an example of this. Let's see. There's a lot of different mechanisms. I'm looking to see if there is. Yeah. There are some examples. I'm just looking for some good ones. Here we go. Actually, this is okay. Very clear demonstration with a controlled force. That's what I'm looking for, is a controlled force. There's multiple things that are happening there all at the same time. But this will give you a pretty good idea of what the force is and what the result is.
This is one of the millions of new and used cars you can find on Auto Trader.
So the interesting thing there does show you sort of the progression. The 850 rod was quite strong. A lot of their examples here, especially the surprise there being the rod in 68 being the strongest out of the bunch, and the BMW 530 rod being the weakest. The 530 being a 2000s era German car. You very quickly see why the performance engines in these had better components, and some of the stuff that's put into just the normal pedestrian cars are not even in the same league. Even though they're both connecting rods, their material strength under load is vastly different. So the 850 was completely overbuilt for normally aspirated application. Same kind of idea with the M3, but the 60s motor being built to withstand far more torture and torment is very interesting. So much bigger, heavier part turned out to be stronger. The Nissan turns out to be much weaker, and there's a lot more behind that, but it gives you at least a reasonable frame of reference with some consistent testing to understand a couple of the failure points in a connecting rod under torsion, or under tension rather than, I was hoping that would be under compression because that would give us some idea, but this is the yield strength that we're talking about. That was where they started to yield was very different, and a lot of them broke at the same place. So a lot of them, the more modern materials, the higher carbon steels that are used in the, or the higher alloyed steels that are used in the performance engines from the M series, they tended not to break at the piston end. They tended to break. The limiting factor was your bolt holding the two, the big end together, as the Brits call it. So there's a lot of importance there for a lot of reasons, but it gives you kind of the relative scale of steel here versus just hot rolled 1020 steel versus 4140 quenched and tempered is significantly stronger. So this is why steel can be so widely different on the same scale. So can't say the Russians never did anything useful for us. They have some examples of materials that you can kind of run through the virtual tester. That's not, that'll help maybe give you some sort of a sense of relative scale. We're going to do some actual tensile testing. And I don't know what your schedule is like for the labs. But there's a few different regions of this curve, and this is where we're probably going to end up spending most of the remainder of our time today, is trying to understand these different regions. These curves look a lot different for metals compared to polymers. The metals have a noticeable necking that happens. The polymers really don't do the same thing. They narrow, and then they have chains that align, and then finally you overcome the bond energy of those individual chains and they start to rip apart. But the case of like a steel or an aluminum is typical of what you're going to see here. So you're going to have an elastic region where nothing changes. You're going to have a plastic region start, so you're going to have a yield somewhere up probably around here or so. You're going to have a yield strength. You're going to have the tensile strength. What's called the ultimate tensile strength is whatever the highest point is on the graph. That's the ultimate tensile strength. This is going to allow you to see what the highest stress the material can possibly take before failure. This region is the necking region. So there's kind of an elastic region here. There is a plastic region here. There is a sort of necking region here, all the way up to failure point. And failure is the ultimate destruction of the material. So this is usually a sharp curve and it comes to an abrupt end. The neck concentrates the stress because that area gets narrower and narrower and narrower. So as the area goes, because the stress is dimensionally proportional to, so this is dimensionally equal to, force over area. And let's make sure it's being shared correctly. It looks like it's not. Of course not. There we go. So the first region here is this elastic region. The second region is the plastic region. The yield to failure region is the third over here. And the stress is dimensionally proportional to force over area. As that area gets to be smaller, the force can be greater and greater and greater and greater. So the stress is dropping, but the stress increases to a certain point. Then as that area starts to decrease, this stress begins to decrease again, even though the force is becoming less proportional to the area overall. So the force doesn't get higher and higher and higher and higher. It's a matter of that area getting smaller and smaller. And so there's a difference between what's called true stress and engineering stress. This is what we actually measure on the device because the area cross-section is changing throughout the course of this region. So everywhere in here, anywhere that even if you're stressing loading the material up and then unloading it, loading it and unloading it, what that can look like is all along the path, you load it up, let's say to here, and then relax it. Then you load it up. We get more movement of the material, you unload it, and it's going to come back down on this same path. You load it up, more plastic deformation, same slope down again, load it up again, all the way up to the ultimate tensile strength, and unload it. It's going to come back down on the same slope. You load it up, it's going to follow that same line back up, and it's going to continue. There's still some plastic recovery or still some elastic recovery, but even if you load it up again, you're going to follow this same curve. It won't exactly follow this curve. The curve would actually look jagged and horrible, and it would be very hard to understand. So this is, in that sense, probably not an inaccurate representation of what's going on there until you hit here, and then the materials fail. So the idea is you're always going to have some percentage of elastic recovery, even with this plastic deformation, but it's going to be so small relative to the amount of recovery that, or relative to the amount of plastic deformation, the amount recovered overall is going to be very, very small. Once the material gets past that yield strength, you're yielding continually. This is also a thing that happens with something like, in the case of an engine, it's an easy example to use because there's a lot of tension and compression both that has to happen in those. Bolts that hold the heads onto the cylinder, the torque to yield type bolts. I don't know if there is a good example of that or not. Let's see. Yeah, there's some examples. So this one's done pretty well with a graphic, and that'll give you an idea. Rather than some dude just yapping at the camera, which doesn't help. There is a bolt test, but there's a couple good examples, but I think this one's going to be the simplest. Yeah, actually, this is somebody that actually understands what's going on. So let me pull this up. We'll see if we can go through some of his key points pretty quickly.
But been too terrified to ask, etc., specify that you give them a particular torque set And when you do the nut up, obviously you wind it up onto the workpiece. It stretches the bolt, which in this case, pretty serious bolt. It's a M24 grade 8.8 high tensile bolt. So, if you needed to, you could beat a zombie to death with this, I'd suggest. Well, I hope it doesn't come to that, but you could. And, when you've got a particular amount of stretch in the bolt, you've got a particular amount of clamping forces between the washers. And that's kind of nice because it holds your cylinder head onto the block, or it holds the rod end cap onto the con rod, or it holds the crank into the block via the big end cap or something of that nature. So that's the theory. If you're an engineer and you're just designing bolted joints, all you do is you pick the right grade of bolt to deliver reliably the clamping force you need without breaking the bolt or causing it to fatigue in service or something of that nature. And that works pretty well, right? Because cylinder head bolts rarely fail in service and big end bearing caps rarely fail. Con rods rarely fail, at least the bolted joints of con rods rarely fail. When you consider the millions of engines that will start up at any particular hour of any particular day around the globe, it's all pretty reliable. So something's going right out there, isn't it? And there's a few different ways you can tighten these babies up, isn't there? Right? You can just do them by with the nature of the fastener itself, okay? When you look at the torque, what you're doing is the torque correlates to a particular amount of stretch in the bolt, which delivers a particular amount of clamping force. And that would be fine if you could standardize the operating environment of the bolt. But in practice, a great deal of that torque, up to 90% in some cases, a great deal of that torque is devoted just to overcoming friction, right? Overcoming the friction that builds up between the mating faces of the thread on the set screw and the cylinder head or the nut, whatever, if it's a bolted joint, if it's a set screw going down into a head, and also under the head of the bolt itself, onto the piece that's being clamped. There's a great deal of friction, and most of that torque is aimed at overcoming the friction, and only some number, like 20 or even less % of that torque stretches the bolt. So in an environment that's really hard to standardize, like the threads could be heavily lubricated or they could be lightly lubricated, they could just have a bit of mill scale on them like these ones do, they could be heavily corroded, and the job, the piece that you're putting a set screw or bolt down into, like into the cylinder block itself, could have residual thread sealing compound from the last time the engine was rebuilt, sort of thing. So it's very difficult to dial in with precision the amount of friction that the torque wrench has to work against. So torque wrench, not that ideal. Now, the thing Peter talked about here, every gram counts, and you've got to make the bolts so efficient. They've got to be contributing all they can do, because if it's 1 gram heavier than it should be, that's a pain in the ass, and you need, kilos more fuel to get it up into orbit or whatever. Okay, but this is not the case with cars. We're just rebuilding engines here, which is not exactly rocket science. So torque wrenches do a fine job. Angle tightening is more precise, all right? So finally, I guess, let us talk about torque to yield bolts, which this is not, but, representatively, they look pretty much the same, and they're just designed to function a little differently. So let's talk about yield, because yielding is one of those things that every engineer and metallurgist understands, but hardly anyone else does. And it's kind of therapeutic, I think, to learn how to break something made out of steel. The physics of breaking shit, it's always uplifting on lockdown, isn't it? Okay, so basically, this is the guidebook about how to break anything made of steel. When you break a piece of steel, this is a graph, and it's strain across here and stress up here, and all of a sudden everyone's going, oh, Jesus, stress and strain, what's that? Just think about it like stretch and load, because that's basically what it is. And I know if you've been through the education mill, as I have, and had your brain bleeding several times already, you'll know that it's not really stretch and load. Stress and strain are slightly different than that. But for everyone else, they're tantamount to that, okay? So when you break a piece of steel, this is the road that it drives along on the way to failure. And there are several interesting waypoints programmed into the GPS. Yes. The first bit of straight road here is the elastic region of the behavior of steel. Now, obviously, when you get anything made out of steel, you bend it a little bit, you can twist it in torsion, you can bend it like this, you can compress it, you can stretch it, it doesn't matter. If you're in the elastic zone, it always returns to its original size and shape. And obviously, there's a point at which that no longer pertains. And you can play around with an old coat hanger or something and bend it gently and it'll spring back. And then when you bend it, and when you bend it a little bit further, you get into this zone of banana-ramarization, okay? You can do that to your ute chassis. We'll talk about that later in the week. But banana-ramarization is a thing, okay? And basically, this is a yield point, okay? They call it the gateway to banana-ramarization is marked by the yield point, which is also called the elastic limit of the material. And after you get across the border and into this region, from elastic to this region, this is plastic behavior of the material, right? And all that means is some of the deformation is going to stay with the material. You're going to bend it, it's going to be permanent, all right? And you'll notice that there's a slight little notch here. Don't worry about that so much. Many materials don't experience much of a notch at all. They just go from elastic to plastic, right? And then the load keeps going and going and going. Load keeps increasing and increasing and increasing. And you get to this point here, the ultimate tensile strength. Yes.
The new Bearskin Hoodie 4.0 claims to be the most advanced, waterproof, tactical.
And if you've ever broken off a bolt in a head or any of that kind of thing, you will know what this feels like, because you get to the point, you're tightening and tightening and tightening, and the load's going on and on and on, and you're going, yes, just a little bit more, and then the load comes off a bit. This is the oh shit point. You go, oh shit, because you know what's about to happen. Obviously, if the load remains the same at this point, the deformation of the material continues unabated and it catastrophically fails at this point, right? And you felt this because you're tightening and tightening and tightening and tightening, and then all of a sudden it just gets softer and breaks. And that's that bit here, getting softer and breaking. So you felt this, you've been on this road, you've broken the shit out of something important. At least now you know the topography. All right, so with all of that in mind, oh, incidentally, if you banana ramify your ute, you end up here. Somewhere here. Some of this deformation is permanent. You don't break the ute in half, although you could. That'd be entertaining, wouldn't it? But generally, you end up somewhere along the road here, stranded with a ute shaped like a banana. Yes. We'll talk about that during the week. However, we're not here at the moment. What we're doing essentially with torque to yield bolts, torque, which they specify in the manual for these things, is about here. It's at like 31 kilonewtons, which is like 3 tons. So these are very conservatively loaded components, right? 3 tons worth of assembly for 6 tons worth of here, it's going to fail, all right? And that's why they don't break very often, because they're so conservatively tightened. Incidentally, it's going to be about 63 newton meters, which is about 46 or 47 foot-pounds, I think, right, for a M10, grade 10.9 at the assembly torque operating about here. So obviously with torque to yield, what happens is there's a higher torque spec for the material. You end up past the yield point and on the road to ultimate tensile strength, and you stop here. And there's so much bullshit online about why this is so. They talk about greater consistency and clamping forces and all that stuff. The main reason for torque to yield is that you can get greater clamping force out of the fasteners. So you can use smaller fasteners to do the same job, or you can use fewer fasteners of the same size to do the same job. And this is important because in things like cylinder heads, there's not a lot of spare real estate. You know, real estate's a premium in a cylinder head because you've got to have mechanical clamping locations, and you've got to get air in, and you've got to get exhaust out. You've got to have a fuel injector in there. You've got to have mounting posts for the various components, such as camshafts. That's kind of important. And you've got to have valve guides in there, and you've got to have water and oil as well. Like, there's a lot going on in a cylinder head. I know it looks boring from outside, but actually designing one is like playing 3-dimensional chess in the dark. So if you can get away with a slightly smaller cylinder head using slightly smaller fasteners doing the same job, like boys fasteners doing a man's job or something, then that's a victory for design. I think you'd agree. Right, so importantly, 2 things flow on from this torque to yield business, okay? When you get something on the road to Plastic City here and ultimate tensile strength, when you unload it, it unloads elastically, but it does not return to the same shape. So if you bend it, it stays bent. Your ute will remain banana ramified. Your bolt will be stretched, okay? Permanently stretched. And that's kind of bad. Not only does the deformation remain permanent, but the material properties change because the various crystals in the steel have been stretched and they move relative to one another permanently. And that's why you shouldn't use the fasteners again, which I guess is the main problem with torque to yield bolts, which is that once you undo something, you've got to throw those bolts away and go again with brand new ones. Otherwise, it's kind of irresponsible, okay? So that would never work, for example, with wheel studs. What a pain in the ass. Every time you service the car, you need, 20, 24, whatever, new wheel studs. Not going to happen, right? It's for these components that hardly ever get undone, like cylinder head bolts or big end bolts or rod bolts or things of that nature, all right? That's why they do that. And the other problem is it's not that difficult to do the angle tightening thing, okay? But you do need an angle tightening gauge because you don't want to estimate 80 degrees or 65 or whatever. You want to measure it, and you can buy one of those things. It's not that bad, but it adds a layer of complexity. And unless you are a bit of a Jedi on the tools, the harder you make anything, the more susceptible it becomes to failure, okay?
So this is why this is so important to understand this process, because if you've done this, if you've done the work to implement something like this and you've done the torque and then you've done the angle of rotation on a bolt or something, you've maybe brought it up to, somewhere around here. The next time that you try and reuse that, so it'll do some elastic recovery down to here, right? The next time that you try and use that bolt, you now transition through this region for ultimate tensile strength, and it becomes weaker and weaker and weaker and weaker. And to get the same rotation, you're going to be somewhere out here if you don't break the bolt entirely. So reusing something like a torque to yield bolt, it seems like a stupid idea. It was something that confused the heck out of me when I was doing a couple engine builds early on. Why have we spent so much time to torque these fasteners to a certain torque spec? And, let's go up to 85 foot-pounds on all of these bolts in a very specific pattern. And then, you just yank it around about 30 degrees. Never really made sense to me until I understood this portion of the stress strain curve and the behavior of the steel that's involved. because a weaker material or a smaller diameter material that is put up into this region before the ultimate tensile strength, this region is okay. This region out here is bad. The best bad you've ever seen written by a man right there. These regions are of very high importance for a lot of different reasons. So we want to be keeping in mind what the curve is actually telling us about the behavior of the material, and each curve has a little bit different aspect to what it's doing in terms of telling us some information. So the ultimate tensile strength comparison, this is where some of these things matter, whether it's a 6061 annealed aluminum versus an aged 6061. That's quite a big difference. That's more than that's effective doubling of the ultimate tensile strength of these materials. Pure titanium versus a specific titanium alloy, 4140 annealed steel versus a tempered and quenched steel. That's a big window as well. So that's, again, more than, I think, a doubling of the tensile strength. Tungsten is really, really tough stuff. Also very expensive. Titanium alloy is also very expensive. The difference between copper hot rolled and copper cold worked in terms of tensile strength, not as dramatic. Certainly not as dramatic as the aluminum or the 4140 steel. 1020 steel just by itself is going to be a little bit stronger than an aged aluminum. So this is where I say certain grades of aluminum and steel actually can fall pretty close together depending on what the exact grade of aluminum is. There are at least some tensile strength numbers for the fibers of these materials. Wood parallel to the grain is very strong. Wood perpendicular to the grain is very weak in terms of tensile strength. So it doesn't take much to tear it apart that way. So huge difference given the same material. So this is order of magnitude, couple order of magnitude difference, something like 2 versus 100. So a couple orders of magnitude there. The epoxy versions perpendicular to the fiber as a general category are going to be somewhere in here. They're all going to be sort of fairly close in terms of tensile strength. Parallel to the fiber, they're going to be significantly stronger. So somewhere on the order of 30 versus somewhere on the order of 1,000. So in the same performance range as materials. So this is why they need fibers that are laying in all different sorts of directions in the case of the composites in order to transfer that stress around adequately to all of these other materials. And so the actual tensile strength of the individual fibers can in fact be there's a couple versions of carbon fibers and things that can be very, very, very high. But generally when you have the resin in place and they're being tested, they're quite a bit different. So these can be very, 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 very strong filaments of material, but it's very difficult to be able to have them be that strong in all directions. That's why they have to change the direction of carbon layup to make parts as strong as they are. So the ceramics, silicon and aluminum oxides tend to be metal-like. Silica crystals tend to be metal-like. Glass a little weaker than that. And then graphite is very soft. We're talking pencil lead, so the tensile strength of pencil lead. If you guys have ever done SAT or ACT testing, you know that the strength of pencil lead is not all that particularly great. So that's why graphite is very low in terms of the tensile strength. concrete a little bit higher than that. And the polymers, you can actually get some very stiff polymers. Nylon 6,6 is used for lots of things. Polycarbonate, PVC, PET. These are all very common materials for constructing plastic parts out of. High density polyethylene is in there as well. That's more recent. Polypropylene, not really used in a lot of structural applications. This is sort of like trying to machine trying to machine polypropylene is sort of like trying to bathe a cat. It doesn't cooperate very well, and probably you'll end up with a mess. That's about all you'll end up with. Possibly also some bleeding because tools slip off of the highly lubrous surface and things like that. So not really great for that particular reason. Has really desirable thermal properties, being able to be autoclaved, but some of the high density polyethylenes can get close to that. PVC, another one that's up in this range is, and very commonly used. A lot of the black plastic that you'll see in hardware stores for like sprinkler systems will actually be something called PVDF, polyvinyl difluoride. So it's fairly non-reactive. It's fairly UV resistant. That's going to be somewhere in this region as well, up here with PVC and polycarbonate. So it's not really a nylon, but it is a polyvinyl. It's just not a polyvinyl chloride. So it's the polyvinyl fluorides are even more resistant to UV and chemicals and all sorts of other stuff. They're really tough. That can make them a little bit more brittle. That's part of the reason why, for instance, nylons here are very small. But that's also why aramid fibers and things are starting to be used, because they really couldn't do, like they had some versions of what they called ballistic nylon and things, but the difference between the tensile strength, so how much force they can hold in tension between nylon and an aramid fiber, is a long distance. And this is part of the reason why the soft ballistic armors have improved so much, is they've figured out how to use some other materials instead of many layers of nylon. They've been able to thin things down with better fibers, better techniques for layup and all of those sorts of things. So this gets into ductility, and I think this is basically going to be our ending point for today, is the beginning of this part. Plastic tensile strain at failure is something that we can see. It's a it depends on what the material is. A smaller percent elongation at failure is going to be stronger and move a lot less. So this is going to be brittle for one. This is going to be a ductile fracture too. So brittle fracture loads, starts to move, bang, it explodes. That's how ceramics and a lot of hardened metals are more like this. So they tend to have a very small percent elongation. They don't move much in their service application. Other materials, like for instance, if you were building a bridge, let's see your votes in the comments. Would you rather have a bridge that people just pile on, boom, and everybody suddenly falls to their death in the icy water below? Or would you rather hear the creaking as the material loads up and you hear things creaking and popping so people have a chance to get off the bridge before they plunge to their icy death below? So let's have a vote. One for stronger material, more expensive, but fails explosively. Two for a material that fails gracefully, and there's a little bit more warning for what goes on. Let's see what the votes look like. most reasonable people are probably going to pick 2. The natural selection answer would resolve several issues in our community if we were to look at regions like certain parts of Washington and or really either Washington and or California. Then yeah, that might be a useful particular application. California is a beautiful state, just a lot of unintelligence there, broadly speaking. So most people would prefer a little bit of warning for something to fail gracefully. In the event of buildings being ravaged by the forces in these hurricanes, the concrete uses a soft rebar inside so that the concrete doesn't just crumble and have a brittle fracture like case 1. It has rebar in it so that it fails and folds and moves slowly when it fails. And that's part of the reason why the rebar and the rebar structure, how it's secured together, how it's safety wired, all of those things get inspected as buildings are being built, especially in earthquake prone areas. Because if in earthquake prone areas things were built with materials more like case 1, that would be very bad. If they're built more like case 2, that's considerably more useful, because things that fail gracefully tend to not release their energy quickly. That's often when people get hurt, is when there's a sudden explosive release of energy. It's a lot more it's a lot safer environment when things absorb energy slowly. This is part of the reason why your crash structures in your car are designed using materials that behave more like case 2, not so there may be a frame that's made of base material that's more like 1. So the frame itself isn't really moving around. That's really strong, especially in the case of more recent trucks and things that have been built. They're really focusing on making frames stronger, but they still have crash structures that are made like material 2 with a mild steel that's going to fold up, and they design 3D stampings to make it look like an accordion so that the material has a path to follow as it goes along this arc. The material has a path to follow for failure so that they can control where the energy goes, then use the frame and shell that's very stiff to transfer the energy out and around the passenger, literally transfer the material out and around the passengers, around the shell of the vehicle into the back, and then down into the ground behind it if it's in a front end collision. So there's tons more engineering than what you guys probably have thought about that goes into this. So we're happy to get you guys the info you need on some of these kinds of materials. We're going to pick up this comparison here a little bit later, I guess next week. Yeah, and then there's a lot more chaos going to ensue after that. So we're going to continue working on some of these. In the meantime, what questions do you guys have as far as details? I know there's some messages that I need to get to, and I'm going to attempt to get to some of those, but I'm going to be limited on how much of that I can do today. So I know there's going to be some specific messages. I'll try and address those, but other general questions.